Okay, so in this video we're going to be talking about sound waves. Before we get to that, let's just do a few warm-up questions from the last couple of videos we've been doing. So we've talked about, the basics of waves, wave properties, different types of waves, and then basic wave behaviors like reflection, refraction, diffraction, and interference and superposition. Okay, so we can do a few questions just to kind of review those things before we get to sound waves. Okay, so here's a question. It says, which wave behavior is shown in the picture to the right? So based off of what we talked about in the notes in the past videos, you should be able to look at this and identify what type of wave behavior you're seeing. In case you can't tell, this is a wave going from the left to the right, and it's hitting an opening here. Okay, so see if you can answer this question. What type of wave behavior is shown in this picture based off of the notes in the past? Okay, so this type of wave behavior is diffraction, so the answer is C. Remember, diffraction is when a wave hits an opening like this and it spreads out past the opening. Not to be confused with refraction, which is when a wave is traveling from one medium into a completely different medium, and that's what causes the bending. Okay, so this is diffraction, so the answer is C. Okay, so take a look at this question here. In the picture below, which wave behavior is shown? Here we have lines to show a wave traveling from left to right from one medium into another medium. Okay, so pause it here and see if you can answer this question. What wave behavior is shown here? Okay, so based off what we talked about in the last question, hopefully you got this correct. The answer is B, refraction. When a wave hits the boundary between one medium and another, typically you either have reflection or you have refraction, or you can have both actually. And so it's definitely possible for a wave to come in and some of it to reflect and some of it to refract. If you imagine like looking at somebody at an angle through like a glass window, some of the light is being reflected off the glass and some of it is being refracted and going through the glass. Okay, and so you might have seen that if you've ever tried to look at somebody through a window and you see a partial reflection on the window. So just to do one more question, this is an example where we have a wave coming in. I'm going to give you the answer for the first question. By the way, this is definitely refraction because we can see the wave is bending. We talked about that before. But it says a wave travels from a denser medium into a less dense medium. State the wave behavior shown in the diagram, that's refraction, and state whether the wave will bend towards or away from the normal. Okay, so remember that whenever a wave travels from a less dense medium to a denser medium, from a denser medium into a less dense medium, it always bends away from the normal. In other words, the wave should be closer to whichever side has more density. And so basically the wave should probably bend something like this. Let me just... Okay, so basically the wave after it goes in the medium should do something like this, where the angle from the normal on this side is bigger than the angle from the normal on this side. In other words, it bends away from the normal because on the other side of the medium there's less density, and so it bends away from the normal. Okay, so this slide is just kind of a review of the things we've talked about before. We talked about wave properties, what is a wave, types of waves, parts of a wave, the wave equation, and then the different types of wave behaviors. Okay, so we're going to talk about sound waves today. And sound waves are a specific type of wave. And you can see here in this animation here, there's a speaker, and these dots represent, let's say, air particles or air molecules. And basically, as the speaker plays a sound, it vibrates, it pushes in and out on the air, and it creates the sound wave. And you can see it's a longitudinal wave. This is not a transverse wave, it's a longitudinal wave. And so remember, sound is one of the few waves that is a longitudinal wave. And so instead of crests and troughs, you get compressions and refractions. And you can see the spaces where the wave gets bunched up, that's a compression, and where the wave spreads out, that's a refraction. And so sound is caused by vibration, the vibration of something, whether it's water or air or some type of medium. Okay, so if you imagine listening to music out of a speaker, the speaker vibrates and it pushes on the air, and the air carries that wave outward. The air is the medium in that case, and then it carries it outward to your eardrum, and then your eardrum starts to vibrate, and your brain interprets that vibration as sound. Okay, and so sound waves, again, one of the most common types of longitudinal waves, as you can see. This is another example of an animation from a tuning fork. Again, this is not a very good animation, but you can see when you play the tuning fork, when you hit it on the desk and it vibrates, it pushes on the air and it creates this type of longitudinal wave. And any type of musical instrument you can think of basically does the same thing. If you pluck a guitar string, the string vibrates, and as it vibrates, it makes the air molecules around it vibrate, and that those air molecules carry this longitudinal wave. And that's how we perceive sound. And so sound is always a longitudinal wave that requires some type of medium to carry that vibration, which is why it's impossible to hear any sound in space, because in space there is no air, there is no medium, it's just a vacuum, and so sound does not exist in space. Okay, now we've talked about frequency before, which is basically the number of waves that pass a point in 1 second. And we've talked about how the unit of frequency is the hertz, and I've shown you, high frequency waves versus low frequency waves. Now, when it comes to sound, the way you interpret frequency has to do with something called pitch. And so, when we think about, two sounds, the one that has a higher frequency, we say has the higher pitch. And I will put a link to a video here in just a second so that you can actually see, or I should say hear, what sounds at different frequency sound like. And so as you watch the video, you can see as the frequency gets higher and higher and higher what that sounds like. Okay, so frequency has to do with what's called pitch. Okay, and of course, sound waves also have some type of wavelength and some type of amplitude. We've talked about that before. So if frequency has to do with pitch, what does amplitude, what does amplitude have to do with? So we would say you perceive the frequency of a wave as a particular pitch. The higher the frequency, the higher the pitch. The lower the frequency, the lower the pitch. Okay, so what affects how loud a sound is the amplitude. We talked about in a past video, but remember, amplitude has to do with the amount of energy stored in a wave. Okay, so bigger wave, higher amplitude. Okay, higher amplitude, more energy. In the case of a sound wave, we perceive that amplitude as loudness. Okay, so there's lots of different types of waves. If you think of a water wave, a water wave with a bigger amplitude just means it's taller. A light wave with a bigger amplitude is brighter. A sound wave with a bigger amplitude is louder. Okay, so just remember that there's a link between frequency and pitch, and there's a link between amplitude and loudness. And so here you can see, these two, I'll mark them. These two waves right here have the same frequency. I can tell by looking at them that they have the same frequency, but this one clearly has a higher amplitude and therefore has a higher sound, or I should say is louder. Whereas these two waves have the same amplitude. We can see, remember, the amplitude is from the rest position up to the crest. Okay, so this vertical distance is the amplitude. These two waves have the same amplitude, right? But this one clearly has a higher frequency because there's more waves in the same amount of time, and so this would represent a higher pitch. Okay, so make sure you understand how those two things are linked. Okay, so just a quick example. We've got 4 different wave pulses here. Which of these sound waves would be the loudest, and how do you know? Okay, so to answer this question, you have to think, well, what properties of a sound wave affect how loud it is? And the answer to that question is the property that affects how loud it is the amplitude. In other words, we need to know, to answer this question, which of these waves has the highest amplitude, and we can see just by looking that B and D, it looks like have the same amplitude, and that is the highest amplitude. Okay, The second question says, which of these sound waves would have the lowest pitch? And so to answer that question, you would have to think, okay, so what is, what factor of a sound wave affects the pitch? And that would be the frequency. The lowest pitch corresponds to the lowest frequency. And so remember, frequency is how many waves pass a point per second. Okay, in other words, which waves are the most bunched up? And just looking at these waves, it appears to me that, just kind of looking at the spacing between these waves, it appears to me that A and B, so actually C and D, I misread the question. Look, C and D would have the lowest pitch, okay? And the way I can tell that is because when I'm looking at this, I'm looking at the wavelength. Remember that wavelength, if wavelength is high, that means frequency is low. In other words, the more spread out the wave is, the lower the frequency. And so I'm looking at the spacing between two crests. I'm looking at that spacing there, that's a wavelength. That spacing there, that's a wavelength, and then here, that's a wavelength, and then here. And if I want the lowest pitch, I want the lowest frequency. That means the biggest wavelength, and I think C and D have the biggest wavelength, and therefore the lowest frequency, and therefore the lowest pitch, because pitch and frequency go together. Okay, so hopefully that made sense. That's just a pretty simple example. Let's do another one, I think. Actually, before we get to any more examples, we're just going to move on to one more property of sound that we're going to talk about, and that is called the Doppler effect. Now, I said a second ago this is a property of sound. That's actually not true. Okay, I should tell you up front that the Doppler effect is a wave behavior. Okay, and when I say wave behavior, I mean it is a behavior of all waves. It could be light waves, sound waves, water waves, whatever. Okay, X-rays, microwaves, whatever. We're talking about in the context of sound because that's a very common example, but it is important that you understand it is a wave behavior that's common to all waves. There's lots of situations where you talk about the Doppler effect in the context of sound. There's also lots of examples where we talk about the Doppler effect for light, and I might mention that later, but first we'll talk about the Doppler effect in the context of sound. Now, you can read the definition of the Doppler effect here. It says the Doppler effect is the apparent change in frequency. Remember, by the way, that frequency has to do with pitch of a wave when the source of a wave, so whatever is emitting the wave, that's a typo. That should say moving. Okay, so ing, moving, towards or away from an observer. Okay, the apparent change in frequency, that is the apparent change in pitch of a wave, when the source of a wave is moving towards or away from an observer. So the most common example that everybody has heard is if you've ever heard like an ambulance or a police car with a siren going, passing you on the street, when it's coming towards you, you hear a higher pitch. When it passes you and starts to move away from you, you can hear the pitch go down. And you've probably heard that before. I'll put a link to a video so you can hear what that sounds like. But almost everybody has heard the Doppler effect before, most likely with a siren. And the reason the Doppler effect exists, and again, this is not just for sound waves, this is for any type of wave, but we can see in this diagram that this ambulance is emitting a sound wave in all directions. If you've got two people, two observers, one over here on the right and one over here on the left, let's call the one on the left A and the one on the right B. Person B, if the ambulance is coming towards them, you can see that on this side, these sound waves get bunched up. Okay, so I can't read my handwriting. Let's try that again. Bunched up. Okay, because the source of the wave is moving in that direction, you can see the waves get closer together. Okay, if the waves get bunched up, that means less wavelength, that means higher frequency. And so person B is going to hear a higher frequency than person A. Because person A is over here on the left and the ambulance is moving away from them, the waves on this side get spread out. Okay, and because they get spread out, the wavelength goes up. That means the frequency goes down. That means they hear a lower pitch. Okay, and so this is known as the Doppler effect, the apparent change in frequency of a wave when the source of a wave is moving towards or away from an observer. Now, you might ask, why does it say apparent? Well, because the truth is the frequency of the wave does not actually change. The person in the ambulance doesn't hear any change at all. It's only based off of the observer, if you're moving towards or away from the observer, that you actually hear or experience that apparent change in frequency. And again, we're talking about the Doppler effect in the context of sound, but it is true for all waves. All waves experience the Doppler effect. So that's a wave behavior just like reflection. All waves can reflect, refract, diffract, interfere, and experience the Doppler effect. Okay, so I'm going to erase what's on the screen. There's some videos here that I would love for you to check out related to the Doppler effect. They're very, very interesting. And so you can see and experience what the Doppler effect is. I will put those links up. This is just another image showing you examples of the Doppler effect. In this example 2, it says, based on the picture to the right, explain where a person should stand to hear a higher pitch. Okay, so to answer this question, remember higher pitch corresponds to frequency. So we want to know, where would a person have to stand to hear a higher frequency? Well, the frequency is going to be the highest where the wavelength is closest together. Okay, and so they would have to stand over here, okay, so that the fire truck is going towards them to hear the higher pitch. And again, that is because of the Doppler effect. So if you were asked, what wave behavior is this talking about, this is, of course, the Doppler effect. Okay, and then just one more example. Again, this is an easy one because we've talked about this before. In this picture, who will hear a higher pitch sound and why? What wave behavior is shown here? This is obviously the Doppler effect, and the person hearing the higher pitch sound is person A, because you can see the police car is playing a siren as it's going towards them. The waves get bunched up on the left, and because they're closer together, the wavelength is smaller, and that means the frequency and therefore the pitch is higher on the left, where person A is standing, compared to the right. Okay, so those are the basics of sound. You do need to know that sound is caused by vibration in some type of medium, that it's a longitudinal wave. You need to know that we perceive frequency as pitch, we perceive loudness or amplitude as loudness in the context of sound, and that the Doppler effect is a wave behavior that applies to all waves, but we talked about it in the context of sound, and it's the apparent change in frequency of a wave when the source of a wave is moving either towards or away from an observer. Okay, so I'm going to stop the video there. In the next video, we'll be talking about light. Please let me know if you have any questions.